In the next proposition, I'm going to give a convergence result for the subgradient algorithm. So under some natural conditions, I'm going to show that the sequence Vk defined in the subgradient algorithm converges to the optimal value of the problem. In the setting of the previous proposition, assume that the sum of alpha k, where k runs from 1 to infinity, is equal to infinity. And the limit of alpha k as k approaches infinity is equal to 0. Then the sequence Vk converges to the optimal value V bar of the problem. So here in this proposition, we have this hypothesis, and we can easily find a lot of examples of sequences alpha k not satisfy these conditions. For example, if we take alpha k, let alpha k be 1 over k, then obviously this condition is satisfied, and also this condition is satisfied. Another example is alpha k here is given by alpha k is 1 over square root of k, and as you can see, both of these conditions are satisfied. Okay, so let me go ahead and give the detailed proof of this proposition. So recall that Vk is given by this. Vk is the mean of f of x1, f of x2 up to f of xk. And V bar is the optimal value of the problem. That means it is the infimum of f of x, where x runs in Rn. By the previous proposition, zero is less than or equal to Vk minus V bar, and this is less than or equal to the distance from x1 to S. Again, here S is the set of all optimal solutions of the problem, and here we have the square sign plus L square times the sum of alpha I square, where I runs from 1 to k, and everything is divided by 2 times the sum of alpha I, where I runs from 1 to k. Okay. Now, since the limit of alpha I or alpha k doesn't matter when as I approaches infinity is equal to 0, if we multiply by L square, we have this. Then this limit L square times alpha I, where I approaches infinity, is also 0. Okay. Now I'm going to take any epsilon greater than 0. Okay, so I'm going to take any epsilon greater than 0. There exists a natural number k naught such that L square times alpha I is less than epsilon, and this is true for all k greater than or equal to k naught. So the idea is over here we see that L square here can be multiplied to each alpha I square, and then we separate L square times alpha I square as L square times alpha I, and then we multiply by alpha I. And this is less than epsilon whenever k is greater than or equal to k naught. Okay, so then we will get this. For any k greater than k naught, we use this estimate and get this. This is Vk minus V bar, and this is less than or equal to. Now I'm going to separate the numerator by this. This is the distance from x1 to s square, and then add L square times the sum of alpha I square, where I runs from 1 to k naught, and then we divide by the same thing at the bottom. 2 times the sum of alpha I, where I runs from 1 to k, and then the second part is this L square times the sum of alpha I square, where I runs from k naught plus 1 to k, and here we divide by the same thing. Okay. Now observe that under this, the right hand side is less than or equal to the distance. We keep the first part. And then here we replace this by the sum of alpha I, where I runs from k naught plus 1 to k, and we multiply by epsilon. Okay, so this is how come this is true? This is true again because over here we can multiply L square in and get L square times alpha I square. Okay, so it's L square times alpha I times alpha I, and then we replace L square times alpha I by epsilon and end up having this. Okay, and note that the top here is less than or equal to the bottom. Okay, because this is the sum from k naught plus 1 to k, this is the sum from 1 to k over 2. The fraction here is less than epsilon over 2. Okay, so again this is the sum where I runs from k plus 1 to k. This is the sum where I runs from 1 to k. So the whole thing here will be less than or equal to the distance from x1 to s square. We keep the first part. And then we replace this by epsilon over 2. Okay. So now observe that the top here is the numerator here is a fixed number, while the bottom goes to infinity as k goes to infinity. Okay. So since we have this limit as k approaches infinity is equal to infinity. Therefore, this sequence converges to 0 as k approaches infinity. Okay, then we get this lim as k approaches infinity, dx1 to s square plus l square times the sum of alpha I, where I runs from 1 to k naught. Here we have square over 2 times the sum of alpha I, where I runs from 1 to k. This limit is 0. Okay. Therefore, we can use the definition of limit again. For that epsilon, then there exists k hat that is greater than k naught, such that the distance from x1 to s square plus l square times the sum of alpha I square, where I runs from 1 to k naught, over 2 times the sum of alpha I, where I runs from 1 to k. This is less than epsilon over 2 whenever k is greater than or equal to k hat. Okay? So whenever k is greater than or equal to k hat, you will see that vk minus v bar here is greater than or equal to 0, and this part is less than epsilon over 2. Therefore, we will see that vk minus v bar is less than epsilon whenever k is greater than k hat. Thus, 0 is less than or equal to vk minus v bar, and this is less than epsilon over 2 plus epsilon over 2, which is epsilon whenever k is greater than k hat. So for any given epsilon greater than 0, we have found a natural number k hat greater than k naught, such that this is true. Therefore, the limit of vk as k approaches infinity is equal to v bar. So we have proved that the sequence vk converges to the optimal value v bar as k approaches infinity, and the proof is complete. So we have proved that under the following conditions, the alpha k is not summable, and also the limit of alpha k as k approaches infinity is 0. So under this hypothesis, we proved that the limit of vk as k approaches infinity is equal to v bar. Okay. So the sequence vk defined in the subgradient algorithm converges to the optimal value of the problem. Now it is interesting that if we impose a stronger hypothesis, we will see that the sequence xk defined by the subgradient algorithm also converges to an optimal solution of the problem. Okay, so what are the assumptions? So if we assume that, again, we keep the first assumption, that means alpha k is not summable, but this sum is less than infinity. That means alpha k square is summable. Okay? Then obviously this condition is satisfied, because from here you will see that alpha k square approaches 0 as k approaches infinity, and therefore alpha k converges to 0 as k approaches infinity. So at first we will have this. Okay, so then we will get this. And then at the same time, we also see a very interesting result, that is the sequence xk defined by the subgradient algorithm converges to some optimal solution of the problem. Okay, so let me go ahead and state this important theorem. Suppose that the sequence of the step size alpha k satisfies these conditions, again, I just repeat what I wrote earlier. Then the sequence Vk converges to V bar, and the sequence xk, again Vk and xk are defined earlier by the in the subgradient algorithm, converges to some optimal solution x bar in S. Okay. So, for example, if we take alpha k to be 1 over k, then as you can see that both of these assumptions are satisfied. Okay, so I'm not going to give the detailed proof of this theorem. You can find the proof in several books. In particular, you can find it from theorem 4.27 in the book An Easy Path to Convex Analysis. And applications, actually. By Mutapcic and myself. Okay, so again, this is a very interesting result, but the proof is rather involved. So I skipped the proof of this theorem. To understand the complexity of the subgradient algorithm, I'm going to look at a particular case where the sequence of step sizes is a constant sequence. Okay, so let's look at this proposition. Suppose that alpha k is equal to epsilon, and epsilon here is a positive number for all k in n. Then there exists a constant c greater than 0 such that 0 is less than or equal to Vk minus V bar, and this is less than L square times epsilon whenever k is greater than c over epsilon square. Okay, so over here L is a Lipschitz constant of f. Okay, and by the standing hypothesis, we see that f is a Lipschitz continuous function. Okay, so let me go ahead and give the detailed proof of this proposition. So recall that we proved earlier that 0 is always less than or equal to Vk minus V bar, and this is less than or equal to the distance from x1 to s square plus L square times the sum of alpha I square, where I runs from 1 to k, and everything here is divided by 2 times the sum of alpha I, where I runs from 1 to k. And observe that in this situation, alpha I is equal to epsilon for all I in n. So this is equal to the distance from x1 to s square plus L square times k times epsilon square, and everything is divided by 2 times k times epsilon. Okay, so now to make the notation simple, we let a be the distance from x1 to s square, and from here we will see that 0 is less than or equal to vk minus v bar, and this is less than or equal to a over 2 times k times epsilon, and then we add the second term here, which is what L square times epsilon over 2. Okay. So now observe that a times a over 2 times k times epsilon is less than the first term here is less than L square times epsilon over 2. This is true whenever k is greater than a over L square times epsilon square. Okay, so we simply solve this inequality for k. So you can multiply both sides by 2, and then we get k greater than a over L square. We keep L square, and then here we have epsilon, and here we have epsilon. That's why we get this. Okay. Therefore, if we combine this with this, we will see that 0 is less than or equal to vk minus v bar, and it's less than or equal to a over 2k times epsilon plus L square times epsilon over 2, and the whole thing will be less than L square times epsilon over 2 plus L square times epsilon over 2, and we end up having L square times epsilon, and this is true whenever k is greater than a over L square times epsilon square. Okay, so at this point we only need to let c be this constant a over L square. Okay, then we will see that this is true whenever k is greater than c over epsilon square. Okay, so the proof of the proposition is complete. But let me go ahead and talk about what we can see from this proposition. Okay. So in this proposition, we observe that vk minus v bar is less than L square times epsilon whenever k is greater than c over epsilon square. So to make it simple, what if we assume that L is equal to 1, okay, and also c is equal to 1, okay? To make it simple, let's go ahead and assume this, okay? So then what happens? You will see that 0 is less than or equal to vk minus v bar, and it is less than epsilon whenever k is greater than 1 over epsilon square. Okay, now if we want, and as you know, vk is used to approximate the optimal solution v bar. Okay, so what if we would like to guarantee an accuracy of 0.01? Okay, how many iterations is needed? So in this situation, epsilon is equal to 0.1, and we want vk minus v bar to be less than 0.1. So under this proposition, we will see that in order to guarantee that kind of accuracy, k is greater than 1 over epsilon square, and over here we can easily compute and get 100. Okay, so to guarantee an accuracy of 0.1 here, we need 1 over epsilon square, that is 100 iterations. And therefore, the convergence is slow in general, okay? And people often say that the convergence of the subgradient algorithm is 0, 1 over epsilon square, or 0, 1 over square root of k. To say that, roughly speaking, in order to guarantee the accuracy of epsilon, we need 1 over epsilon square iteration. Okay. So I have completed presenting the unconstrained version of the subgradient algorithm. So we have seen the subgradient algorithm used in order to solve unconstrained optimization problem. So now a question is, how can we use a similar method to solve constrained optimization problems? That means we want to minimize a convex function f of x subject to in omega. Here f from Rn to R is a convex function. And omega is a non-empty closed convex set. And again, we use the following standing assumptions. F is Lipschitz continuous. In Rn with Lipschitz constant, we can assume and we also assume that this problem has an optimal solution. Okay, so the set of optimal solution is non-empty. Okay, so in order to solve this optimization problem, people use the so-called protracted subgradient method. So this is the so-called the protracted . And this algorithm is defined very, very similarly to the subgradient algorithm. We only need to add an additional step where we use the Euclidean projection. Okay, so the algorithm is defined as follows. So at first we pick x1 in the constraint set omega, and then we define xk plus 1 as follows. So at first, we perform the subgradient algorithm as usual. That means it is xk minus alpha k times vk, and again vk is a subgradient of the function f at xk, and alpha k is a step size. But then we use an additional step. We project this to the constraint set omega. Okay, so xk plus 1 is equal to the Euclidean projection of xk minus alpha k times vk to the projection set omega. Okay, so this is omega, and this is xk minus alpha k times vk, and then we find xk plus 1 by computing this Euclidean projection. And if you watch my my earlier video lectures, you're going to see that if omega here is a non-empty closed convex set, the Euclidean projection P by x omega is always non-empty and unique. Okay, whenever x is in Rn. Okay, so the subgradient algorithm is well defined, and again over here where Vk is chosen in the subdifferential of the function f at xk, and also alpha k here is greater than 0. So the projected subgradient algorithm is defined like this, and the convergence result for the projected subgradient algorithm is very, very similar to the convergence result of the subgradient algorithm. Okay, so let me go ahead and talk about a proposition we proved earlier for the subgradient algorithm, and now it holds as well for the projected subgradient algorithm, and then everything will follow similarly. Okay, let xk be the sequence generated by the projected subgradient algorithm. Then we get this estimate norm of xk plus 1 minus x square is less than or equal to norm of xk minus x square minus 2 alpha k times f of xk minus f of x plus alpha k square times L square. And this is true for all x in omega and for all k in n. So the difference between this result and the result we proved earlier for the subgradient algorithm is here it is true for all x in omega, and in the similar result we proved earlier is true for all x in Rn. Okay, so we only need to replace x in Rn by this condition. Okay, and the proof of this proposition is very, very easy. Okay, so proof. Now here if we let gk plus 1 or gk, so we let gk plus 1 be this, be xk minus alpha k times vk. Okay, so this is actually what we defined earlier for the subgradient algorithm. Okay, so it follows from the proof we performed earlier for the subgradient algorithm, we will get this. Then norm of gk plus 1 minus x is less square is less than or equal to norm of xk minus x square minus 2 alpha k times f of xk minus f of x plus alpha k square times L square. And this is true for all x in Rn, but in fact over here we only need to use for all x in omega and for all k in n, because we are not concerned with x outside of omega. Okay, now we're going to take a very important property of the Euclidean projection presented in my lecture before. So this is a subset omega And here we assume that omega is non-empty, closed, and convex. So this is x1. This is the Euclidean projection from x1 to omega. And this is x2. And this is the Euclidean projection from x2 to omega. And we proved earlier that we always have this. The projection, the distance between this and the projection from x2 to omega is less than or equal to norm of x1 minus x2. That means the Euclidean projection mapping is non-expansive. Okay? And obviously, if x belongs to omega, then the projection from x to omega is just a singleton x. Okay? So with that, we will see the following. Then we will see this. The Euclidean norm of xk plus 1 minus x squared. Okay? So as we know, xk plus 1 is the projection of gk plus 1 to omega. From the definition of the subgradient algorithm, we know that xk plus 1 is just the projection of xk minus alpha k times vk to omega. And over here, this is just gk plus 1. Therefore, we get this. Okay? And then x, again, x is in omega. So x is the projection from x to omega. I already mentioned that earlier. So this is just the projection from x to omega square. Okay? And now we use the non-expansive property of the Euclidean projection and see that this one is less than or equal to norm of gk plus 1 minus x squared. Okay? And then as you see over here, this is less than or equal to norm of xk minus x squared minus 2 alpha k times f of xk minus f of x plus alpha k squared times L squared. And this is true for all x in omega and k in n. Okay? So the proof of the proposition is complete. And as you can see, so in the subgradient algorithm, after we prove this proposition, we get important estimates for the difference of vk and v bar. And over here, we can also define the same thing. If we define v bar, vk by the mean of f of x1 up to f of xk as usual, and we define v bar by the optimal value of the problem. That means the infimum of f of x, where x runs in omega. So under the standing assumptions, we will get the same thing. We will get the same thing by using this proposition. That means, for example, we can show that 0 is less than or equal to vk minus v bar and less than or equal to the distance from x1 to s squared plus L squared times the sum of alpha I, where I runs from 1 to k, this is square, and over 2 times the sum of alpha I, where I runs from 1 to k. Okay? And from there, we will continue to get similar convergence results for the projected subgradient algorithm. Okay? So, for example, if alpha k is not summable but square summable, then we can show that vk converges to v bar, and at the same time, xk converges to some optimal solution of the problem. Okay? So in the next lecture, I'm going to talk about some examples of the subgradient algorithm. Okay?